I'm exploring how the n_neighbors parameter in scikit-learn's spectral_embedding function affects dimensionality reduction. It's all about understanding how changing the number of neighbors considered during graph construction impacts the final embedding. Let's dive in. This is the core question. I need to evaluate different statements about how n_neighbors affects the results of the spectral embedding. This statement suggests that increasing the number of neighbors makes the resulting embedding smoother and more interconnected. I need to determine if this is true. Here, we're considering the opposite. What happens when fewer neighbors are used? This statement proposes that a fragmented embedding will result. I'll decide if this is correct. This is an opposite claim. This statement claims that n_neighbors hardly matters. I need to check its validity. This statement claims that n_neighbors controls the number of eigenvectors. I need to examine if that is the case. This is the title, highlighting the main topic: the effect of the n_neighbors parameter on spectral embedding. This section indicates that I need to understand how spectral_embedding works and how the graph is built using the nearest neighbors. I see. This parameter is the control knob for how many nearby data points we consider when building the connections in our graph. A higher value means I'll connect each point to more of its neighbors, leading to a denser network of connections. Conversely, a lower value means I'll only connect each point to a few of its closest neighbors, resulting in a sparser network. This algorithm is like a magic trick. I take the graph we just built, where each data point is a node, and connections represent proximity, and I use some fancy linear algebra involving eigenvectors of the graph's Laplacian matrix. I won't bore you with the details, to transform those points into a lower dimensional space. The key is that the algorithm preserves the relationships between those points captured by our graph. This is the result, the transformed set of data points in the lower dimensional space. Because the algorithm uses the connections in the graph I created with n_neighbors, the resulting arrangement of points in this new space directly reflects the influence of n_neighbors. For example, a large n_neighbors would create a globally cohesive embedding, while a small n_neighbors would lead to a fragmented embedding reflecting only local relationships between points. The n_neighbors parameter doesn't directly alter the number of dimensions in the reduced space, but it powerfully shapes how the data is arranged within that reduced space. It controls how much the embedding shows the global picture versus highlighting local clusters. I see this step as the heart of the process. The n_neighbors parameter tells the algorithm how many closest data points to consider when building a network of connections between them. Think of it like deciding how many friends each person has in a social network. A large n_neighbors value creates a densely connected network, where many connections exist. A small value creates a network where connections are sparser. This network is crucial because the rest of the algorithm operates on this network's structure. This is where we use some cool math. Imagine, we have a matrix that represents our network's connections. The eigenvalue decomposition finds special numbers, eigenvalues, and vectors, eigenvectors, that reveal important information about the network's overall structure. These eigenvectors are used to create the final reduced dimension representation. This is the final output. We use a select number of the eigenvectors found in the previous step to create a new, lower dimensional representation of our data. This lower dimension representation captures the essential structure of the data while discarding redundant information, enabling data visualization in lower dimensional spaces. The Laplacian matrix is a mathematical representation of our network. It captures the connections between data points, and its structure is directly related to the network we built in the previous step. The choice of n_neighbors significantly affects the Laplacian matrix, ultimately influencing the embedding. This is where we feed the algorithm the initial data that we want to reduce in dimensionality. We input the raw data points. This title describes the core topic: how the n_neighbors parameter affects the results of the spectral embedding technique in machine learning. Spectral embedding is a dimensionality reduction method. It transforms high-dimensional data into a lower-dimensional space while trying to preserve important relationships between the data points. Imagine connecting each data point to many others. This results in a densely connected graph. A higher n_neighbors value means I consider more points as near neighbors when creating the graph that underpins the spectral embedding. The embedding then reflects a smoother, more unified view of the data because the global relationships between data points become more apparent. Now, let's connect each data point to only a few of its closest neighbors. This leads to a sparser graph, where the data points are more isolated from each other. The resulting embedding will highlight local structures. Clusters of closely related data points will be emphasized while overall global structure may suffer. It may even become fragmented. With fewer connections between points, low n_neighbors, the spectral embedding algorithm gives more importance to the local neighborhood of each point. This can lead to a more fragmented embedding where the relationships between different parts of the data are less clear. A higher n_neighbors value will make the underlying graph denser, creating a smoother embedding. The global connections between points are prioritized, giving a more holistic view of the data. It's as if I'm looking at the entire landscape instead of just small pockets. This phrase introduces the core topic: how changing the number of nearest neighbors affects the spectral embedding algorithm. I'm focusing on understanding the algorithm's sensitivity to the n_neighbors parameter in Sklearn's spectral_embedding function. This is crucial because it determines the structure of the graph used for dimensionality reduction. This question asks how adjusting the n_neighbors parameter, the number of nearest neighbors considered when building a graph from my data points, alters the outcome of the spectral embedding method. I need to consider how graph connectivity changes with this parameter. This statement says that if I increase the n_neighbors parameter, my resulting embedding will be smoother and better connected at a global level. I'll need to think about why a higher value makes the graph denser, increasing global connectivity, which translates into a smoother embedding. A decrease in the n_neighbors parameter should result in a more fragmented embedding, which is good for highlighting local structures. I'm focusing on why a smaller n_neighbors value creates a sparser graph and why a sparser graph better preserves and highlights local structures in the final embedding. This is an important thing to understand. This suggests that the n_neighbors parameter does not significantly matter in spectral embedding, which is incorrect. I know this is wrong because the parameter heavily influences the graph structure, which directly affects the resulting embedding. This statement wrongly claims that n_neighbors dictates the number of eigenvectors. I know that is wrong. In reality, the number of eigenvectors used is controlled by a different parameter, n_components and is completely unrelated to n_neighbors itself. I'm analyzing how the n_neighbors parameter affects the results of spectral embedding, a dimensionality reduction technique in Sklearn. I'll explain how changing this parameter alters the resulting embedding structure. This question explores the core concept of how the number of nearest neighbors considered during graph construction influences the final low-dimensional representation of the data. Increasing n_neighbors means each data point connects to more neighbors, creating a denser graph. This leads to a smoother embedding, better reflecting the overall structure of the data. The embedding emphasizes global relationships between the data points. Think of it like adding more bridges between islands. The islands become more easily accessible from each other. When you decrease n_neighbors the graph becomes sparser. The resulting embedding focuses more on local clusters and neighborhoods, potentially leading to a fragmented representation of the data. Each data point is less connected, much like small, isolated islands with few bridges. This statement is incorrect. I've learned that n_neighbors significantly affects the graph structure and, therefore, the resultant embedding. It's a crucial parameter that we can't ignore. Nope, that's not correct. The n_neighbors parameter controls the graph construction, while the number of eigenvectors used is determined by a separate parameter, n_components. These are two distinct aspects of the algorithm. I'm analyzing how the n_neighbors parameter changes the results of spectral embedding, a dimensionality reduction technique. It's all about how many nearby data points we consider when building a graph to represent the data. This graph's structure directly impacts the final, reduced dimension representation of the data. We'll see how changing this parameter affects this representation. Pretty cool, huh? I'm posing this question to check your understanding of how n_neighbors affects the spectral_embedding function. We'll examine how changing the number of neighbors considered affects the final embedding of the data. This will reveal your grasp of the core concepts. Get ready to test your knowledge. With a high n_neighbors value, I get a denser graph. Many connections between data points. This leads to a smoother embedding, where global relationships between points are more clearly shown. Think of it like this: a tightly knit community. Everyone knows everyone, reflecting a cohesive structure in the embedding. This is a result of a higher n_neighbors value in the spectral embedding process. A low n_neighbors value results in a sparser graph, fewer connections between data points. This will lead to an embedding that captures local structures in detail because it only uses a limited number of neighbors in the vicinity of each data point. Think of it like having many small, isolated groups rather than one big community. It's the opposite of a high n_neighbors scenario. When I use a low n_neighbors value, I end up with a fragmented embedding. It is because the graph representing my data will have many separate, weakly connected components. My embedding will reflect these isolated structures. It's like having a bunch of tiny islands instead of a large continent. The focus is on local details rather than the big picture.